Hi everyone, we are Chenyue and Qingzhou. We are glad to present our work AngleCAD, led by Dr. Liu, with joint works from Brinda, Mehra, and Dr. Alvaro Cassinelli. And this gives is quick demonstration of our project. In summary, it is a set of surface-based 3D modeling techniques based on foldable screens. Nowadays, the widespread and decreasing cost of 3D modeling software and digital fabrication machines are pushing a trend of casual maker. They started to attract interest from non-technical or untrained individuals to fabricate their custom designs. However, the function and the interface of current software, such as Rhino, are not really intuitive and friendly to novice users. Also, they are known to have a high barrier of entry due to the difficulty of learning 3D manipulation and operations. There are existing approaches attempting to make 3D modeling easier for novice users on different hardware or interface. For example, TouchSketch introduced simpler control widgets for modeling on touchscreen. MixFab make use of mixed reality with a see-through device to engage users in personal fabrication. Mockup Builder attempted to create a semi-immersive virtual environment with widgets and additional physical button. The last example, by 3D, focused on commanding finger and pen gestures. Most existing approaches are limited to 2D interfaces. Therefore, we present a novel approach by utilizing foldable phones. In particular, its physical fold angle to create a 2.5D space for more direct interaction with 3D shapes, while displayed is through the two screens. Being able to create simple 3D objects on mobile devices could also facilitate making in various contexts and activities. Our approach also further opened up new ways of using foldable phones, while existing works on foldable phones focus more on window management. For example, an early work, FoldMe, mainly designed foldable screen with dynamic size and folding shape, focusing on how different way of folding could enable the transfer or access to information. Similar idea of using foldable screen to display a 3D space has been proposed in Foldable 3D. However, the interaction on user experience has not been fully explored. We designed the techniques by taking inspiration from woodworking process, which is a physical shape creating craft that works primarily with surface and edges. This could help us create more intuitive techniques based on the surface and folding angles of foldable phones. Current foldable phones in market can either only be folded in one direction of 180 degrees or have software constraints such as turning one screen off automatically when the fold angle reaches a certain degree. Therefore, we designed a custom hinge with 3D printed parts and metal wires to allow the two phones to be freely folded in 360 degrees. We also implemented a simulated perspective view for user to facilitate global positioning of virtual objects in space in order to explore their shape, find and bring the view the paths of interest. It will track users' eyes position and give users the control to switch between face tracking mode and fixed viewing angle mode. Basic orientation control, rotating, translating, and scaling can be done in one or two finger gestures. The angle between the two phones will start to take effect here. During rotation, the fold angle will determine the rotation axis, which is perpendicular to the operated screen. During translation, the object will be moved following the drag direction and in parallel with operated screen. You can also see that on top of the screen there is a third view, providing a view angle perpendicular to both screens. To distinguish from rotating and surface modification, we require a cross-surface pinch to scale the model. After scaling, the user can click the button Record Real Measure. It will record the scale of the model, which can later be recovered by clicking the Recover button. This way, we can differentiate scaling the view from changing the actual size of the model. The first shape modification technique is cutting. We mimic the use of surface for cutting wood. Here we use the viewing screen also as a cutting surface. The intersection between the virtual object and the screen is marked in red. After adjusting the position, clicking a cut button on the cutting screen will trim the object. To achieve direct manipulation on surface, we designed the snapping function to attach surface to the screen. This automatically enters orthogonal projection mode and displays a real scale measuring grid. After snapping, user can push the object towards the edge and extrude the snapping surface along the other screen by dragging the extrude handle. Snapping also enables another two direct manipulations to modify the surface: tap, taper, and drill. After an object surface snapped on screen, a single screen pinch gesture is used to taper it, or user could press a drill button to create a hole in the center of the screen, and then pull the handle on the other screen to control the depth of the hole. Next, Qingzhou will present our experiments, findings, and the conclusion.
So hi, I'm Cyan. So we conducted a preliminary user study with the AngleCAD prototype, and we tried to find the answer of those questions. Firstly, our goal is to evaluate the effectiveness of the AngleCAD approach for 3D manipulation. And we also want to evaluate what is the user experience of our techniques. And lastly, we would like to gain insights for designing physical plus 3D manipulation. So we recruited 7 participants with various levels of experience of 3D software. 2 of them have never used those software. 2 of them are novice, and there are 2 medium-level users and 1 expert. So we asked participants to perform 2 main tasks in the study. The first task began with the user watching a demo of a person building a vase using the AngleCAD system. He or she was then asked to build a similar vase that did not need to follow the procedures in the demo. So after building the vase, the second task for the user was to create his or her own model in 8 to 10 minutes. They were encouraged to build whatever they want. Finally, the users will fill in questionnaires and complete the interview with the experimenter. So participants were able to learn from the demo video and build a similar vase. So although they appropriated the tool and came up with their own order of building it, some started from the middle, some did the drilling first. During free exploration, we can see with only quite basic functions provided in our system, participants were able to build a variety of objects, including a phone support, a human face, a sword, a building, etc. So the overall experience of AngleCAD is positive, with the interaction being intuitive and providing a good way of object visualization in 3D space. Having the physical surface to provide a support and haptic feedback was found to be one of the main advantages of our approach. Participants enjoy the process of manipulating models by directly touching them. According to the survey, the operations of object manipulation are easy to learn and to perform, including translation and scaling. Rotation got a bit difficult due to the lack of direct manipulation on the third view, which is perpendicular to both the screens. So the operation for the object modification was less easy to learn and perform, with extrude being the hardest. This may be due to that extrusion was done by pushing the object inwards from the screen, quite different from what people are used to do. And among all the functions, snapping is one of the is actually the most popular one. Users describe it as has clear indication on later option and being unique and do not exist in other CAD systems. So we also want to introduce some of our key insights from the experiment. For example, users tend to gain a sense of 3D not by adjusting their perspective, but by rotating the model, which means constant phase tracking to update the view is unnecessary and even causes the view to be unstable. And we also found that the orthogonal projection on the top of the device is very useful for precise modification. The user can control the exact dimensions of the surface while adjusting the height from the side screen. We also discovered that 90-degree is the most frequently used angle, which is maintained by the participants for the majority of time because they can better understand the 3D space and operations they can do in this angle. Lastly, although we tried to mirror most operations on both screens, they were used differently by the participants in the study. They frequently used the left as the main screen for observing the object and on-surface operations like cutting and snapping, while they also frequently used the right screen as the assistive screen for input like the trackpad on our computer. And for depth control and also for like depth control when extruding or drilling. So the lessons we learned for physical plus screen manipulations are that firstly, for physical manipulation, including fold deformation and using touch gestures for rotation and translation are kind of imprecise. So the potential solutions for this can be that we need to design a mechanical hinges that provide haptic feedback by clicking or momentarily looking at the standard angular positions, such as 0, 45, 60, or 90. And secondly is the touch control. So it is about digitally snapping the input values into intervals or integer. And another issue found was that there is an interference between the GUI operations and the physical manipulations. So they are basically the errors due to touch gestures. So the implication for that is that designers might need to design for error prevention, considering the holding postures for such hybrid interfaces. And so thirdly, current users are not used to having the physical configuration of displays affecting the digital content. So the rotation and extrusion were considered relatively difficult or confusing. So here is some room for improvement. There can be more dynamic visual feed forward and feedback to guide users through those operations. And lastly, for the lack of direct manipulation from the third view for rotation, as we know, foldable phones only have 2 screens. So maybe this could be potentially provided by adding one more screen perpendicular to both existing screens, but at a cost of increasing complexity. So for conclusion, our approach was shown to be intuitive and effective for viewing and manipulating 3 objects, with particular advantage in providing physical support and tactile feedback in the Z dimension. Our surface-based interaction techniques were easy to use and perform, although additional feedback is needed to strengthen the link between physical manipulation and its effect on visual content. So, however, we are still excited that we made AngleCAD to this step because we believe it will open up new user scenarios for foldable mobile devices and lead future research on hybrid interfaces that combine physical and GUI operations. Thank you.